All right. So, there is a bonding theory or a bonding perspective that people use to explain what is occurring when bonds, covalent bonds, form. And we've kind of talked about this a little bit. Two hydrogens come together, overlap, and form a large space where electron density can be shared. Does that make sense? Yeah, that's fine. You can even think of this the orbital on the hydrogens as 1s orbitals, right? We've heard of that. For something like HF, hydrogen fluoride, the hydrogen brings its 1s, right, to the fluorine, and the fluorine has, this is the orbital diagram for fluorine, 2s, 2s2, 2p5, and it would like to have 2p6 to have a noble gas electron configuration. And so you can imagine the hydrogen sharing electron density and overlapping with that p orbital of the fluorine, all right, to make this kind of an orbital here. Okay, valence bond theory, that the last orbital that has the electrons in it is forming the bond, right? And this works, but only kind of. And why doesn't it work? Well, here's the situation. If you look at a compound like H2S, hydrogen dihydrogen sulfide, right? Or hydrosulfuric acid when put into water, right? Sulfur's in the middle, hydrogen's here, and then two regions of non-bonding electrons. Now, when we talked about this compound before, we would say that there's 4 regions of electron density, and those 4 regions of electron density would be 109.5 degrees from each other. All right? And that is the case for water, right? This angle here we said was a little less than 109.5, 104.5 actually, right? But for hydrogen sulfide, this angle here actually becomes about very close to 90 degrees. And so valence bond theory fits for this kind of a compound. However, valence bond theory doesn't work when we look at something like CH4. CH4, right? We're taking carbon and 4 hydrogens, and the angle here is a very strict 109.5. And if we think about carbon, it's a orbital diagram. Carbon is a helium core. This is the electron configuration with a 2s2 and a 2s2 and a 2p2. All right. So, and if we were to draw the 2p orbitals, x, y, and z, and we were to show the hydrogens coming in with their, their 1s orbital, so this is a hydrogen, 4 of these hydrogens need to bond to this carbon. So this is our carbon, and these are the p orbitals. And we only have 2 electrons in our 2p, and we need a total of 6. So this is going to be, we need a total of 8. Sorry, so this is going to be 2, 3, 4, 5, 6. Sorry, we need a total of 6. Yeah, 6 more, or 6 total. Sorry, 2, 3, 4, 5, 6. With these 2, that makes our 8, right? So we need 1 maybe hydrogen to bond there, 1 hydrogen to bond here, and then the other one, where's it going to bond? Over here, and maybe over here. And what that would look like is some sort of a carbon here with 2 hydrogens that are linear with each other, and then one that's kind of in a T-shaped, and then one that's going away from us in the plane. And so this wouldn't look like anything that had this angle here would be 180 degrees. These angles here would be 90, and this angle going in the back there would be 90, right? But that's not what the compound looks like. The compound looks like this. It looks like 109.5.
So what happened?
Well, valence bond theory just doesn't work for most molecules. We need something else. We need something that's called a hybrid overlap theory. And this hybridization theory, it basically thinks about all of the available atomic orbitals and mixes them together, hybridizes them together. And these hybrid orbitals, we name them based on the combination of atoms or of the orbitals that come together to form the new hybrid orbital. And they are redistributed to the locations where electron density is needed. So, for example, if we're going to have a carbon bond with 4 hydrogens, all right, what we need is we need that carbon to have 4 regions of electron density extending to these hydrogens. 4 regions, right? How did I know it was 4? Because the chemical formula for the compound that we're trying to draw is CH4, right? Carbon needs to extend to those 4 regions. And then I can think about the electrons that carbon has available to it, actually the orbitals that carbon has available to it. Carbon has, we can look at the orbital diagram for carbon, right? It has a helium core and then a 2s and then 3 2p's, right? So, this is for carbon again. So if carbon needs to extend 4 regions of electron density, it takes 4 of its atomic orbitals, one of this S, that's one of the P's, third one, and then the fourth one. So it takes all 4 of those, combines them together, and forms 4 hybrid orbitals. All right? Now, 4 hybrid orbitals that come out of the combination of one S and 3 P's, we name sp3 hybrid orbitals. So what we're saying is that the carbon atom takes its 4 orbitals, combines them together, and extends these hybrid orbitals. Now, these hybrid orbitals are a mixture. They don't look like S and they don't look like P. They're a mixture, and they look something like that. They have a big lobe, kind of like the S, but they also have a little bit of P character. And these 4 regions are extended, again, trying to spread out evenly as possible. Okay? And then the hydrogen bring in their 1s's, and the bonding occurs between the hydrogen, the 1s's of the hydrogen, and the hybrid orbitals that the carbon made. Now, the hybrid orbitals are called sp3 hybrid orbitals. sp3 hybrid orbitals. Okay? Do you know why we name them sp3 hybrid orbitals?
Not really.
Well, it's because carbon took one of its S and 3 of its P's all together, combined them together, and extended those orbitals, those hybrids, out towards the atoms that it was going to bind to. Does that make sense?
So you named them sp3 hybrids because they were made of an S and 3 P's.
That's right. That's right. Very good job. Good job.
Thank you.